Hello everyone and greetings from Germany. My name is Markus Frank and I am a PhD student at the University of Stuttgart. I am glad to present the topic of formal specification of parallel patterns for the Palladio component model using hierarchical queuing PetriNets in the context of FAACS ECSA 2020. But before we jump into the topic, I would like to give you a brief overview of my daily business. Therefore, I would like you to meet John. John is a data analyst and runs intensive statistical algorithms on large datasets. Lately, their BI system reached a maximum utilization. That was when John came to me. I'm a software performance engineer. He asked me if I can tell him how the software will behave on different hardware environments, so that they can get the right environment for their needs. So I started to model the software using Palladio, a state-of-the-art performance prediction tool. Using Palladio, you need to specify the software behavior, the hardware characteristics, and the user behavior. Afterwards, you get performance results and you can do what-if analysis. Today, I want to focus on the specification of the software behavior using Palladio. Because John's BI system was written as highly parallel application, I needed to consider that in the software models as well. So let's have a look at an example. Palladio uses UML activity diagram-like syntax to specify the software behavior. So to specify two concurrent tasks, you need to specify each thread individually. Here, calculation A and B. We ignore the annotations within the actions for now. To tell Palladio that it runs in parallel, we add a fork action in the synchronization point to indicate that both threads are forked and in the end synchronized again. So we want to wait for both tasks to be completed before we continue. However, if you have a parallel system, you need to specify hundreds or thousands threads manually. This is not practical, so we came up with a parallel pattern catalog for the performance engineer. At the bottom, you see how the parallel loop pattern, which is the most common one, would look like. You simply annotate the add parallel stereotype and specify the thread pool size. When we showed that to other performance engineers, they liked the simplicity of the approach, but were confused how the underlying behavior is specified, which is important to correctly model the software and to use it for testing as well. Therefore, in this work, we formally describe the behavior of parallel patterns for the domain-specific language of the Palladio component model. Thereby, we assume that all patterns can be broken down to parallel loops or sections. Thus, we only consider thread-based parallelism and no message passing based parallelism. For the specification, we use hierarchical queuing PetriNets. Okay, next we will have a look at two already specified language concepts of the Palladio component model, loops and forks. Due to the limitation of time, I will not explain the foundations of hierarchical queuing PetriNets here, nor will I explain the foundations of the PCM here. For this, I referred to the paper or to the links provided below. So first, let's have a look at the loop action and how Heiko Kocolek specified them in his PhD thesis in 2008. Unfortunately, I also do not have the time to explain the specifications and the math below the nets. So we only focus on the nets here. But I provide them to better follow the explanations along with the paper. So let's have a look at the PetriNet. This is only a subnet of a bigger set of hierarchical queuing PetriNets. So whenever we enter a loop here, a token is fired into the first place. The loop itself contains of three parts. The first one is the entry part. The second one is the loop itself. And the third one is the exit. So when a token is in the first place here, transition is fired and a token is placed in the second place here. This second place represents the loop condition. So whenever the loop condition is satisfied, transaction 3 will fire and will return the token to a higher net. If the condition is not satisfied, we enter the loop body. The loop body is represented here by this place with ID 2 and represents its own subnet. So we place a token in the subnet. When the subnet is finished, it returns the token and it's placed in this place 1 here again. And the loop condition is re-evaluated. So next, let's have a look at asynchronous forks. Asynchronous forks work a little bit different, but we again have these 3 parts. The entry point here, the exit point, and the actual fork body. So the difference to the loop here is that whenever a token is placed in the first place, we immediately return the token to the higher net. And we also place a token in all the subnets, which represents forks, at the same time. When the tokens return from the subnet, we simply destroy them. This way we can assume asynchronous behavior. So now let's have a look how parallel loops work. Parallel loops are actually a combination of forks and loops. And in general, we separate here between synchronous and asynchronous loops. What you can see here is an asynchronous loop. And it again consists of these 3 parts: the entry point, the exit point, and the loop and the loop body. So in this asynchronous scenario, whenever a token is placed in the first place, we immediately return it to the higher Petri net. And at the same time, we enter the loop body and we iterate until the loop condition is fulfilled. When the loop condition is fulfilled, we destroy the token. In each loop iteration, we fire a token in a subnet. And thus we execute the subnet. When the subnet returns, we again destroy the token. Synchronous loops look a little bit different. Here we do not return the token in the beginning, but we again have the loop, which fires the tokens into the subnet. And whenever the tokens return from the subnet, we basically collect them here and we have a waiting condition until all tokens from all subnets are returned. And then, and only then, we continue and return 1 token to the higher net. So, let's wrap it up. I explained to you the issue when modeling massive parallel applications and the problem when using the parallel architecture pattern catalog. So to face these problems, we first had a look at 2 already specified concepts using hierarchical queuing nets, the forks and the loops. Next, we used these 2 concepts to define and specify the behavior of parallel loops and sections. Therefore, the software performance engineer can now specify thread-based parallelism and performance prediction models. And he can understand the semantic now and can use it for automated testing of the simulators as well. Okay, that's it from my side, and I'm looking forward for the discussion round, and thank you for your attention.